Hello everyone, today we will be talking about Dijkstra's algorithm for solving the single source shortest path problem in a weighted graph where all weights are non-negative. The algorithm was proposed by the well-known computer scientist Dijkstra in 1950s, and until today it's one of the most commonly used algorithms in practice. Consider a group of friends who start their day with an early workout at the gym, and after their workout, they intend to walk to different buildings on campus to attend their classes. There are direct paths between some pairs of buildings, and it takes a certain amount of time to walk from one building to the other one. For example, 5 minutes from the gym to the computer science building. And because of the cold weather, these students want to take the shortest path from the gym to their destination, to get there as fast as possible. And they're trying to find such shortest path. As we've learned in previous classes, we know that we can model such problems using graphs. Consider a graph G with set of vertices V and set of edges E. Each vertex represents a building on campus, and each edge represents a direct path between two buildings. Also, weight of each edge represents the walking duration of corresponding direct path. Given such a graph, we are interested in finding the shortest path from the gym, that is the source vertex S, to all other buildings. Dijkstra's algorithm provides us with a solution for this problem, which we call the single source shortest path problem. And it works in two phases. Phase one is initialization. In initialization phase, first we set the distance of vertex S from itself to be 0, which is obviously correct. And since we don't know the distance of all other vertices from S, we set them to be unknown and denoted by infinity. Also, in initialization phase, we categorize all vertices into two groups, group of unvisited vertices and visited ones. Initially, all vertices are unvisited. Now that we have the initial setup, we can start the second phase of the algorithm, which is a series of iterations. Each iteration corresponds to a vertex. And it works as we see briefly in this example. In the first iteration, we go through the list of all unvisited vertices, S, C, L, and P, and take the one with the shortest known distance from S. In the first iteration, that would be S itself. We call it the current vertex, and we examine all unvisited neighbors of the current vertex. In this case, it would be C and L, and we check if we can find shorter path from the source node to these vertices with current vertex as the immediate predecessor. For example, consider C. Currently known shortest distance from S is infinite. However, if we want to reach it with S as its immediate predecessor, we can get there in 0 plus 5 minutes. So 0 plus 5 is equal to 5, which is smaller than infinite, so we have a shorter path. We obtain a shorter one, so we can update it. Same reasoning goes for L. Now that we have examined all unvisited neighbors of the current vertex, it's safe to move the current vertex from the list of unvisited vertices to the list of visited ones. At this point, we're done with vertex S. That means we have the shortest path to reach it, and we know we cannot use it anymore to obtain shorter paths for reaching other vertices, because we have examined all of its neighbors. In the second iteration, again, we go through the list of all unvisited vertices, C, L, and P, and take the one with the shortest known distance from S. we call that vertex the current vertex, and we examine all unvisited neighbors of the current vertex. For example, consider L. The currently known shortest distance is 10, but if we want to reach it through C as its immediate predecessor, we can get there in 5 plus 4, which is equal to 9 minutes, and that's smaller than 10. So we found a shorter path with C as its immediate predecessor. We can update it. And same reasoning goes for M and P. Now we have examined all unvisited neighbors of the current vertex, so it's safe to move it from unvisited list to the visited list. And we proceed with the next iteration. Go through the list of all unvisited vertices, find the one with the shortest currently known distance from S, call it the current vertex, and examine its unvisited neighbors. In this case, only the shortest path for P is updated, and we keep going for all vertices until all of them are visited. So there are no unvisited vertices anymore, which indicates the termination of the algorithm. Now that we know how the algorithm works and what the general idea of algorithm is, let's put these steps next to each other in the correct order to obtain a pseudocode for Dijkstra. Dijkstra's algorithm works in 4 main steps. The first 3 correspond to the initialization phase, setting the distance of source vertex from itself to be 0, set the distance of all non-source vertices to be infinite, and marking all vertices as unvisited. The fourth step, which itself consists of 3 smaller steps, corresponds to the second phase of the algorithm. That is the list of iterations, the series of iterations. The first step in each iteration is finding the one with shortest currently known distance from S. Second step would be examining all unvisited neighbors of the current vertex and making an update if required. And finally, after examining all neighbors, it's safe to mark current vertex as visited and remove it from the unvisited list. Is this clear for everyone how the algorithm works? Any questions at all? Great. So far, we have only computed the length of shortest distance from the source vertex. How can we efficiently modify the algorithm we just saw to obtain the actual shortest path? Let's take a few minutes to think about it, and then we can discuss it together.